Hello, good afternoon, y'all. In this fourth episode, we are going to have a look at finding elements in our list. In the last few episodes, we've built our list to store a bunch of elephants with their name and their color. In between the last video and this one, I actually added another field, which is the year. Where did I go with my script? So when I run this script, it pretty much lists all the elephants that I have added to my list, right? So doesn't particularly matter what the names are, but how would I go about finding, for example, in which year a specific elephant was born? Now, in order to refresh our memory a little bit, let's have a look at how our list looks like, but I will draw it in a very simplified way this time. So let me jump to some paper. Alright, so what we have here is we have our elephants list. Making sure. And we have those 5 elephants here. These are Chili, which color is red, and born, I have to cheat, sorry, give me a sec. I can't see them. 2013. We have Elvis. I have not come up with those names, which is white. From 2016. We have Zoe, which is blue. From 2018. We have Archie. My handwriting is actually terrible. And we have Phil Snow, which is white, from 2015. And in our list implementation, we had already shown you the head pointer, and we had in between these an arrow pointing to the next one and one to the previous one, between all of them. And we won't bother with all the intricacies or how we build this list anymore for now. We also had this tail pointer, which points to the last element. Let me make this black. There we go. So that's our list that we had. Now, how would we find the year for Archie, for example? Well, there are 2 ways of finding it at the moment, right? We can go to the start of the list, look at our first element, see whether our name matches what we're looking for. If not, we go to the next elephant. Does this name match? Yes, then we can return it, and otherwise we can't, and we need to jump to the next element, and so on and so on. So, because we never know how many items we have to go search through, our search space is n, the amount of elements that we have. If you remember or not, the big O notation for this would be ON. And ON basically says that at worst, we need to search through this many elements, I was going to say elephants, in order to find the right one. Which of course isn't great, right? I mean, if with 5 elements doing 5 string compares on just the name of the elephant is fine. But if we have 1,000,000 elements, or say we have 5,000 functions like the PHP language has, then doing this every time you want to find something, of course, takes up a lot of time, and that is not great. So, what are better ways of doing this? Well, there's several ways. One of them is construct a binary search tree, which is a valid solution, but I'm not going to talk about this in this episode. We might get back to that at some point later. But what a very common data type to use here is something called a hash. And a hash is basically a data structure that uses a mapping from your name to a number so that it can instantly look up this number. So another way how you can guess how this list looked like is pretty much as follows, right? So instead of having 1 to 5 here, what we can also basically say, and how do you call that, links in between them, you can also just see this as an array, where we have Chili, Elvis, I really can't write today, Zoe, Archie, and Phil. And basically have those 5 elements in the list. Now if we would already know which number it is, and we start counting a 0 here, then if we know the number that belongs to Archie, in this case 3, then of course we can find it immediately. But how do you map those names to these numbers? Well, there are different ways of doing this. Well, one example that you could do in this case here is we count how many letters the name have. So in this case, Chili has 5 letters in the name, Elvis has 7, Zoe 3, Archie 6, and Phil Snow has 9. Now, how many elements do we have? We have 9. So what we can draw is draw up the following table, right? So we draw a table between 9 or 0 and 10. You'll go find out that I run out of space soon. I'm just drawing the different boxes with the different lines. Of course, I miss one. Now, Chili had 5 items, so we can put Chili here. Zoe had 3. Archie had 6. Phil Snow had 9. And which one do we miss? Elvis had 7. So now we filled up our table here. And by going from the length of a name, we can instantly find our element in our table, right? And that is quite a quick way of doing that. And in a very simple way, actually, when PHP first was built as a language, this is exactly how finding the elements worked. Now, of course, we do get a problem where if we would introduce another elephant, say we would add an elephant called Bluey. Well, Bluey has also 5 characters. So what we'd have to do is we have to make this into a list, so that we can store them both. And of course, instead of this list, what we can do is use the list that we've already used in our previous few videos. Now, of course, there's a few issues here. What if we get an elephant that has a very long name that has more than 9 characters? Well, then it doesn't fit here, right? So let's have an elephant called Archimedes. Again, I can't spell that and probably not write it correctly either. And how many letters have that? Well, it has 4, 5, 6, 7, 8, 9, 10. But of course, we've only reserved 10 spaces. So how do you fix that? Well, the typical way of doing that is using a modulo. So if you have a limited set of elements in your list, then what you can do is do the modulo of how many elements you have. Let's say 10 in this case. And of course, if you calculate 10 modulo 10, which is the expression for that, you get 0. So Archimedes would then map to this spot. Sorry, it just falls off the screen here. And so this allows you to add many more elephants, even though their numbers might always map at the same place. Now, of course, doing the string length isn't great. But let's start with that and see how we can implement this specific type. Alright, so back to my screen where we have our code, where I currently have this LL list, our linked list implementation. But what would we need to store for this hash? As this is called a hash table. you hash a specific name to a specific number, which then forms the index in a lookup table, which then will be backed by linked lists. Now, first of all, we are not going to use linked list directly here, we're going to use a hash. So let me switch. Of course, we need to go implement those in a moment, but let's add that. So instead of a list, we get a hash, we create a hash, and previously what we had used for our destructor for our list, that would call it whenever the list was freed, was by using a destructor. Now the destructor in this case doesn't have to be changed, but of course the name LL_list_detour is a bit old. We probably should name that to just detour. But I'll sort it out later. And then of course all of these hashes need to be, all these lists need to be hashes. And then we can do, for example, hash walk and then a hash detour. So that is our main code. I mean, this isn't hard to just basically search and replace. But let's first have a look at our elephant list detour. So I'm not actually sure why we had an elephant list detour. What a better name would be elephant callback detour, because we already have this destructor, this detour for doing the objected zone, and it's just something that we end up calling, if you remember, from we end up calling that from our list detour, as you can see here in these few lines. It's just our list detour, because it needed to have a generic pointer data type, because our linked list implementation could support more than just elephants. It could support anything pretty much. We had to have this void pointer, which then calls this elephant detour right here. Now, we can leave this, or what we can do is basically create an equivalent function that we use the same for the hash. So we can do it like this, for example. Now, this is technically not nice because we are adding implementation details into our code. But it works, so let me make sure to save that. And then instead of list detour, what we can do here is hash detour. Of course, it is never nice to actually implement the same function twice. Now, there's different ways how you can do that. You can either call the previous function from this function, or as I've done here already, call the same function that actually does the work, or alternatively, you can define a macro if you want to do that. Oh, I can't type again. And elephant list detour. So that pretty much basically maps the name hash detour to list detour when the code is being compiled. So basically what the preprocessor does, it changes what we have, this name here, it actually changes it for the other name, which is handy, but it also makes things harder to debug to use macros. So I'm just going to leave my original code here that actually has a function, because that means we can set a breakpoint in it and everything is going to work as expected. So these are the changes that we made, or the additions we made to our elephant structure. But what we need to do, of course, is actually implement our hash. Now I start out with our list, and I'll just save it as hash, just to see what kind of changes we need to do. First of all, we need to change our preprocessor guard to make sure we only do lists. Our utility methods are going to be the same, but I'm going to skip over the removes for now on. I mean, we can implement that too, but let's leave it for now. Yeah, and that is pretty much it. It's the linked list element callback is going to be a hash element callback, but these items are just the same. It's just slightly different name, because technically they could have different items. Now in our hash itself, we don't have our list elements anymore. In our list itself, well, what do we need to store? Well, we still need to store our destructor, right? The structure that we need for the elephants. sorry, for the element. But what else do we need to store? Well, what we do need to know is how many buckets do we have? How many items where we can store elements in? So in our example, we had 10 elements. So let's see if we can just do that. And we call that bucket count. A specific element, a specific hash index where you put things on is often called a bucket count. And then what else do we have? Well, we need to have this many buckets allocated, and the buckets that we're allocating are going to be lists. So we have the struct list. We need a pointer to that, and how many do we need? Well, we need to have 10 of them. So 10 pointers to a list, but of course this is not nice because now bucket count isn't optimized out, for example. So instead of doing 10 pointers, I'm creating a pointer, meaning that we can allocate those things freely when we want to. And I'm just going to replace all the ella lists that I missed here by hash. Technically, in the prototype definition that we hear, you don't need to actually define the name of the variable. You can just leave it out, actually. I like leaving them in. So there we go. This is our hash definition. So we don't have any list elements here, but we have the amount of buckets, which if we want, we can actually do as an element to our constructor, so that we can define that depending on what we're going to have implemented. Now, same thing with our hash.h. Now, one thing I still need to do here is we need to include our linked list implementation, because we use that for our buckets. Okay, let's do our normal list as well. We save this as hash.c. So what we're going to introduce here, well, we have our hash. We don't need our list elements. We only have our hash itself. So we have our hash, which, if you remember, we had this detour and the amount of buckets. Now we do this in a pretty similar way. We allocate our structure, and of course these things are just slightly different. We have our detour, but we also have our bucket count, and our bucket count is buckets, and we then need to allocate our buckets themselves. Now, what do I actually want to allocate here? Do I want to allocate our lists immediately, or do I just want to allocate enough pointers to lists? Now, in order to do some optimizations, we don't actually want to allocate a list yet, because it's a very common thing to have many more buckets than you have elements, because what you don't want to end up with in a situation is where, for example, if there were so many elements with 5 letters in their name, and we had very few buckets, what you don't want, of course, is to have so many items, say 100 items behind 5, because then you have to search through 100 elements again, right? So this is a very common thing that you have, for example, say 1024 buckets for maybe 500 elements. That means that there's a lot less chance of having the collision, notwithstanding our very bad hashing function here, of finding having to loop through our lists. Now, I'm going to cheat a little bit because I forgot what we had stored here. But basically what we want to do here is we want to allocate our pointers, but not our lists. So we do that by doing malloc. And what are we going to... Well, first of all, we need to remember how many buckets we have. So that's the amount of buckets. And then we need to pick our data structure. And if you remember what we were going to store at, we were going to store list pointers. Pointers to our linked list implementation. And it'd be great if we would also null these. Now, to null something, what you can do is allocate them and then set them all to null. It's a very thing to do. Or you can use a different function called calloc, where beyond just allocating, it will also set all the values to null. Alright, so our list detour is our hash detour. And what do we need to do in our hash detour? Well, pretty much the opposite as what we need to do when we allocate something. So we need to free our hash. Oh, sorry. Thanks, Ben. So what we need to do is not only free our hash element itself, but we also need to store all the bucket pointers that we have calculated. So we need to create a little loop here, and loops are always done with I, and for the amount of buckets that we have, for I is 0, I smaller than hash buckets. If our bucket is not null, buckets, a very difficult word to type, buckets, nope, still got it wrong. If our bucket is not null, we can just do that with that. Or rather, we can do if it is null, then we just continue our loop. I am a big fan of jumping out of loops as soon as we can. Then, of course, we need to call our linked list detour on that element or on the bucket. And that will also free the bucket. So that takes care of freeing all the contents of the bucket. But of course, what we also need to do is free our buckets themselves, which we allocated in our constructor. So this pretty much takes the opposite of what we done in the constructor, right? Where we allocated our hash, this line, which we free here, and we free our buckets that we've allocated here. And at the moment, all the buckets are going to be 0 anyway, so the code in here would never trigger, of course. Now, how would adding, just looping over all the elements look like? Well, we implement this hash walk, right? And it's pretty similar to how this works compared to walking the list, except that we have a bucket per list. So what I'll do is copy and paste this. Of course, we don't call the detour. And then what we do, for each of our buckets, we need to walk that list. So we call list walk, and then our bucket list. We call our same callback, and we pass in the same context. Ben is asking a good question. Does the I automatically increment in the loop? No, it does not. So thanks for being my compiler preprocessor here. Luckily, the compiler would have mentioned that to me. So pretty much this is what walking the list is, right? I mean, it does mean that we won't see the items necessarily in the same order that we've added to our hash. Okay, so what would adding a elements to our hash look like? Well, first what we need to do is we need to calculate. Get rid of this. What we need to calculate is we need to calculate from our hash key. So hashes work a little bit different than just lists because each element is defined by a hash key. In this case, it is our key. Then the first thing that we need to do is we need to calculate what the hash index is. So index is hash key function, and we'll switch those out in a moment, and we just fill in the key. Let me just remove the removes for now, because we're not going to use that just yet. Now, once we have our index, what do we need to do first? We first need to make sure whether our bucket has been allocated or not. So if our bucket is null, we need to create our bucket. And we do that by constructing a linked list. And what does the constructor to list take? It was our hash destruction function, or list destructor function, which is, I forgot the name of it, is hash element data detour, right? So that's that. Now, if we know we have this list, because that is guaranteed now, unless we run out of memory and then we have many more other issues, is to then add our elements now to the list. So we can call list add. We add it to our bucket. Oops. So the i's should be indexed here, of course. Did that the wrong way around. And that what we can then do is add our data element to it, which is going to be just data. Now, this technically should be all the code, but let's see how I fared making typos in my code. We added an extra C function, so we need to add that to our makefile. Drumroll, seeing how many items I'm going to get right or not. Okay, we do get some, many errors actually. Alright, so the first thing it says hash.c line 7, conflicting types are hash ctor. We say hash buckets here, but in hash.h we say struct list still. Which of course I misseen. Okay, on to the next one. Now it says struct hash has no member named bucket. Did you name bucket? Yes, that is exactly what I meant. That should fix. See how many more we have. What is our next error? It says comparison between pointer and integer in line 23. Okay, that line 23. That makes sense because we don't need to loop to buckets, but to bucket count. I'm a bit disappointed that nobody caught up on that. Let's see. That should be it, right? What else did we get wrong? Hash line 42. Oh, that should be buckets. And I'm sure I did those wrong here too. How are we doing? So hash add, still we missing our key in our H file. Key. I mean, it'd be pretty awesome if it would have compiled straight out of the box. But that's never the case. What is the next one? I can actually not see. Did I get more errors now? I think so. Hang on. Okay, it talks about our hash key not being defined. We'll leave that to the end, but we need to look at the others. It says in 51 here that llicitor hash element data detour doesn't exist. Which makes no sense, because you see it. Hash element data detour. Oh, it's of course called detour. Nope, wrong phone. Line 51. There we go. It said was another error here. How are we doing? We're getting closer and closer. Okay, of course it gives a warning for all the hash adds because we don't specify the hash keys. So in this case, I'm actually going to use the lowercase variant so that we can actually search these things case insensitively. Why? I don't know, but there is no need for those hash keys to have any relation to any of the data, of course, that we have in our elements. Oh, elephants. Okay, let's see. Getting close. There's only one page of errors now. So our hash detour in line 8. We don't specify how many buckets we want. Let's say we had 10, right? And then the only thing we haven't implemented yet is our hash key function, which is fine because we haven't. And our hash key function is the tricky one we're going to have a look at in a moment. But for now, before we get there, I'm going to cheat and just return 0. That pretty much means that every time we have a hash element, that it shows up in the first bucket. Now that is of course pointless, but it allows me to easily strap to this code. So our program compiles. Does it run? Yes, it seems to run. Excellent. They even show up in the same order, which makes sense because we link them all to the same number 0, right? Do we have any memory leaks? We have no memory leaks. So I'm doing pretty well here, right? But of course, the only thing that we haven't done is implement our hash function. So let's start our debugger. We're starting GDB here, and we set this breakpoint on just before we call the walk here. So which line is that? Using set number in Vim. So that's line 16. So I do break on line 16. We run. And let's see what our elephant hash actually contains. Okay. Let me put it to the start of the list. So what does it say here? Well, we have our hash. What does it contain? Well, the bucket count, which is 10. The buckets pointer itself, and our elephant hash detour. We're not really interested in that in the detour, how many buckets. What we are interested in our buckets themselves. And when we do star, it prints the first element, which is the same thing as doing buckets 0. If we would do bucket 1, we should get null, because we had no element that mapped its index to 1, because we made all of them map to 0. As you can see here. I mean, pointless hash function, but it does do the job. So if we now would look at what we have in this list, sorry, buckets. What do we have in our buckets? I don't remember the name of it, so let's introspect this first. So there's a head and a tail, as our lists have. Our head, let's see what data we have in here. But that doesn't work right because we're using generic data types. So we need to tell it that we actually have stored, we need to tell the debugger that we actually have stored an elephant in it. And you can see here it has chili in it with a color red, which is the first element that we added, and the year. Great, so let's do next to see what we have there. We get our second element, or second elephant, our third one, our fourth one, our fifth one, and then when we do next once more, we should get an error because there should not be any element in here. So that makes sense, right? We have no element in our listing. So everything maps to element 0, which is great. But we want to do something clever here. So what we can do is strlen key. And when we run this now, let me compile this, make, and when we now run our test file, we should get a different output because we only show the elements per bucket. And you see here the different output, right? It starts with the smallest one because that would map to an earlier bucket. So the element for Zoe would map to our fourth bucket because it has 3 characters. Now, of course, what we haven't implemented here is what happens if we add Archimedes. So if we add another elephant, because we know that that is a letter too much, right? Let's call him Pink, because I like pink. He is from the year 0. Let's make it 1 so that we don't inadvertently do a wrong error. So if we run this, if we run make now and we run test, where did Archimedes go? It didn't show up anywhere, right? And the funny thing is, if we run this with Valgrind, we actually get quite a few errors. Because of course what happened is that we get this error here. It says invalid read of size 8 when we do the hash add in line 55. Well, if we turn on the numbers, and we go to line 55, it says here do H buckets and we use I, but I, it says here exactly this address, the address that we're trying to read, is 0 bytes after block of 80 allocated. And this number 80 makes sense because we allocated 10 elements and each element is a pointer, and on a 64-bit machine a pointer takes up 8 bytes. So basically this says we're trying to access something just below a block that we have allocated. And that makes sense if we look at the diagram here, right? Because Archimedes has 10 characters who would be just behind here that we have allocated, so that is just 0 bytes after that. Now, I've already illustrated or indicated how you would solve that, and that is of course by doing the modulo of how many buckets we have. And of course, for that to work, we then also need to pass in our hash itself, otherwise we can't access that. And if we compile this now again and run this test, then Archimedes shows up again. And it shows up first because, of course, the modulo of 10 is 0, and that's why it shows up first. And I also forgot how to spell pink. Let me fix that. So that's how we do simple hashing with elements. And to look at implementation of this, this is how mailing lists will find address email addresses. This is how PHP would find functions in its big function table, or it would use hash tables. hash tables implementation in PHP is a lot more complicated than this, but the same idea is there. There's a way of having a mapping between a name and a pointer. Oh, sorry, a name and this index number. But doing this on the length of the string is not necessarily a great hashing method. If we look at all the English words in the English language, then the rate between them isn't particularly very high, right? I mean, how many words do you know that have 2 characters? Well, there's 12 if you have to go by Scrabble, I believe, right? So if we know that, then using just a string length for 20,000 words is not going to be great, because say that there are 8,000 words for 5 letters, we have to search through this whole long list to do that. Of course, we haven't implemented our searching here yet, because that is a bit trickier to do in this way, because the only way how you standard search with a hash table is by its key, not necessarily by elements in it. Although, of course, if you want to search for that kind of stuff, you sort of need to know how the data structure looks like before it can run this comparison between the key that you pass in and a specific element in our case, our elephant structure. So, how would you approach that is, of course, by allowing a generic way of how you can compare what you're searching for with this element in the hash key. So in this case, we didn't really store this information, right? The only information where we have this is we've only mapped our, we basically hashed our names into a number. That, of course, loses the names. And yeah, that is something that you need to solve in this case. So you can't actually use the simple linked list structure unless you either implement a list that knows the names for each of the elements as well. In this case, that would be the hash key. Or what you can do is create a comparison function that when you walk through a whole bucket, you can call this function as a comparison function. So let us implement that first before we come up with a better hashing function on its own. Of course, we add a new function that is called hash find. And hash find is going to return something, is going to return a void pointer, because we don't care what we store in our hash. So we define our hash. We have our key that we want to look up to, and our comparison function. Hash compare callback. So this, for example. Now this doesn't quite work, because this will only work if our names are the same. So we do actually need to capitalize them correctly, otherwise we won't be able to do this find later. But there's no reason why you couldn't search for the lowercase versions. But let's do it this way now. Now, how is our callback function going to look like? Well, what does it need to do? For our elephant structure is it basically needs to compare our hash key that we can feed it to the callback, and then our elephant structure, right? So let's add our elephant h file. So this is, let's call this int, because we have no booleans, elephant hash match. Let's call it this way. And then we have our hash key. And then we have the void pointer that is going to be our elephant. Because that's the only type that the hash can feed in, right? Because it doesn't know that we're storing elephants. So that is a hash match function. So how to call that? Well, we can do hash find. On our elephants, let's say we want to find Archie. And then as comparison function, we call elephant hash match. I know, running out of space here. We've implemented the hash find here. The only place where we need to do this now is we need to do that in this place as well. So we're going to return a void pointer. We pass in our hash, our key, and our compare callback. But we do need to give that a name. So we have the hash walk here, where I call it hash element callback detour. How did I call this here? Hash element compare. It doesn't particularly matter how we call it, as long as actually it does matter. It needs to have the same name as we use here. No, it doesn't matter. Never mind. Ignore. Hash find. Need to make sure to add it to our list. Hash compare callback. Hash compare callback. Those needs, well, don't have to be the same, but it's better to do. But how do we find our hash compare callback? We do need to define it as well. So we have our element callback, which is a silly name, but we define this void pointer type, hash compare callback. And how do we want that to look like? Well, it needs to have our hash key, which is a constant car pointer, and we have our void pointer, which is our data element. So there we go. Now, how do we implement the find? Well, first thing, we need to hash our elephant name. We do that by the hash key. Then, if our bucket doesn't even exist, so if not h buckets, I should have picked a different word, then we can simply return null, because if there is no bucket with the hash, then there won't be an element in there either. And if it is, we need to loop over this again, like we do with LLS walk, but of course that trick doesn't work here. So really what we need is a function in our list that does the callback, which is fine. So we're simply something to add. So we have our bucket lists, buckets I, and then because we haven't implemented LLS find yet, we also just give it our callback. And this function is going to return either null or an element. Let's see if this compiles mostly. Nope, let me... okay, it says it can't find LLS find. That makes sense because I haven't implemented yet. And because it doesn't exist, we need to... it returns by default an integer. Let me just quickly add our LLS find. So we have walk. And that looks pretty much the same as this one, except for the context. So yeah, in C, if you don't define a data type for returning, it imagines it's an integer. Now, of course, it winds in the llist find that it doesn't know hash compare callback. That makes sense because we're in a list here. So we basically copy and paste this line. Oh, sorry. This line here. Rename it. Now, technically, it is of course not okay to just use a different type, but because its function signature is the same, it doesn't matter. Okay, now I definitely messed up something. What did I mistype? Okay, let's start from the top here. It's just probably a simple typo. Okay, you see what I forgot here is I forgot to add what did I forget? llist find, of course, it doesn't know the hash. It wants to have a list. There we go. Still made many errors. It says in function llist expected to find something. Oh, I see what I've done. I've missed a semicolon here. Okay, now there's only one error still that we get here. Except for not... okay, hang on. What is going wrong here? It says warning passing element 2 from llist find from incompatible pointer type. So we pass in void pointer const_char void. It says node expected const_char. Oh, I see. In our list find, of course, we no longer need to have our key because that's already been reduced to this specific list. There we go. So now the only thing it basically says is that llist find, it can't find because we haven't implemented that yet. And it can't find elephant hash match because we also haven't implemented that. So let's do llist find first. And how do we find something? Well, it is like a walk, but instead of doing a callback for each of the elements, so this is find. What was it called? Compare callback CB, and that's it. So while we loop through this list from the start, if our callback matches, I also need to return a void pointer here because we will return our elements. So if our callback matches, and in this case our callback has the problem that llist find does need to know the key, right? Because otherwise it can't match this, because our callback is going to match our key against our data. And if that matches, then we can return our data. And if not, we return null. But of course, meaning that llist find needs to have our key as well. So const_char key. So what I originally had done in here was correct. Let's see if we can compile this. Okay, I got a few more errors. Okay, in hash.say we say llist find. I'm getting too many screens here. Of course, we do need to pass in our key here. That's what it was warning about. And here it says void value not ignored as it ought to be. Because our callback still don't know what it is, so we need to define that first. So we will do that here. We remember what is the callback was an integer. Our hash match got our key. Did we not already implement this? Yeah, I think we did, didn't we? Yep, it is there. But we haven't implemented it here yet. Okay. So we had defined it, but hadn't implemented it yet. Elephant hash match. I will pronounce this correctly once. No, match. Key, and then we have our void. Elephant. Here we can say struct elephant. Elephant is it's a bit long, isn't it? But that's how you need to cast that. And then if our hash key matches our elephant name, then we return 1, otherwise return 0. Now I have to say something that strcomp, if it matches, it returns 0. It's kind of annoying, but that's how that works. So that's our function there. We call make. Okay, we still got one error. It says hash compare callback wants a void pointer, but our argument is of type int pointer. Well, it needs to be a int pointer because we are going to need to return something from that. So we need to define our hash compare as an integer. Now, of course, that also means we need to do that here. Now it compiles. Want to see whether it works? Well, it should work, and it shouldn't output anything because we haven't done anything in our code yet, right? But we do have this hash find. So let's say that we have our elephant here, and then I thought we had a function to dump the elephant info, show elephant info, that's what it was. Font info, we do E, and then our context, we do something weird, it doesn't matter. Run make, we need to declare E, of course. Struct elephant E. Of course, when we run this, it might actually not work. It does compile. Interesting. And when we run our program, it indeed finds Archie, and it says orange born. Okay, maybe we should make this exclamation mark into an arrow. Try again. Make first. Run tests, and yeah, it finds Archie, right? If we call Archie. What if we do it with a lowercase a? We get a segmentation fault. That makes sense because what we didn't check if we only should show the elephant info if there's actually something found. So we check for the return value. So there we go. Our hash find now works, and if we improve our hash function, which is the last thing that we'll talk about today, to improve that a little bit to something else than simple string length, yeah, that works fine. However, it'd be nice if we could do this on a command line without having to type this every single time, and there's a way for that in PHP, or sorry, in C. You can just pass in the argument handler. Yep. If I spell int correctly, that should do the trick. It gets a segmentation fault because we didn't give it any code. That doesn't find it. If we press A, it finds RG. If we type fill snow, it finds fill snow. So it is the way of doing arguments on the command line is by making sure that your main definition includes argc, stands for the amount of arguments that you get, and then avoid pointer-pointer argv, which has then all your arguments. argv0 is your program's name. argv1 is going to be your first element. So you ought to check for these things. So if argv is smaller than 2, then we show usage information. And the cool trick here is that you can actually use argv here, and then it will always substitute your program name. Exit. So that it remembers that. I'll show you what that means in a moment. Oh, definitely mistyped something. Oh, printf need stdio. stdio. Did it whine about something else? Exit needs a number. It's an error situation, so let's not return 0. And stdlib, it needs to. It is handy that the compiler tells you these things. That is something that is new in GCC 10, I think. So it compiles, let's run it, and it tells you your usage information. Argy finds it, and then the cool thing is if you rename your test program to find elephant, for example, then if you call find elephant, it says usage find elephant, and you don't have to recompile your program, which is kind of a nice trick. But we replace it back to test. Anyway, so that is our implementation done. We have looked at the argument. We have done our very basic hash. I won't say this is the best hash implementation that I've ever made, but at least it works. Now the only thing that we need to do something about is having a less stupid hash function itself. So I shall close down all the other screens here. Now, there's a question, there's a few viewers here in the chat here, is what would be a good way of hashing, what would be a good hashing function be? What kind of things would you need for a good hash function? You'd want something pretty much that uses the whole space, the whole key space. You want it to be unique, uniform spread, and you also don't want it to be slow. A typical way what you can do is you can perhaps use an MD5 sum and pick the last byte. That gives you 16 possibilities for your hash function. Or you can do SHA-256. Those are all really good hashes that have a very wide distribution in your hash space, in your buckets then. But they're also really slow. And that's not great either. So there are a couple of functions. So yeah, in the chat, Pink Emma saying multiply the letters together and truncate. That's not necessarily a bad idea. So let's see how we can implement that. So we start with our let's call it a long, doesn't matter, count, and initialize it to 0. And that our letter itself that we're going to pick, we call it letter. I like naming things useful. And then we can loop over our whole key. Okay, there's some pointer arithmetic involved here, and then we can return at the end our letter that we have done, again modulo with our bucket hash, right? So, which is our bucket count. So what is the operation here? So basically we do letter is letter times C. So that would, for every letter that we have, we multiply our letter by the number of letters that we already have. So let me compile that. Ooh, sorry. Let me go back to my elephant, my test program actually, and I'll back my hash walk again, so that we can have a look at the output. What was our callback again? I forgot. Was it? I need to cheat because I can't remember. Which one was it? It wasn't show elephant info. What did we call this? Was it show elephant? Yeah, I think it was. If not, we can fix that. C undeclared. What did I do wrong? Of course. What we need is, of course, is our result. Oh, bugger. I need to do this correctly by implementing the right things instead of doing things wrong. There we go. That is the right implementation. So this compiles again. Let's run it. Of course. So it first does the archie, and then it does the other elephants, and they all come in a very different order now, right? It has no relation to the string length anymore. So this is probably a much better hash function. It is, however, not a hash function that most people or most implementations use, but it is already much better than using the string length, for example. What a typical hash uses is something called DGB2 that works pretty much the same, but slightly different. So instead of starting with 0, what it does, it starts with this magic number that nobody has ever been able to explain what it is. And then instead of doing the duplication, what it does is it takes what we already have, do it times 33, and then add our letter. So that is actually an implementation that is used a lot, but you see it implemented slightly different. You often see it implemented as this, and it makes perfect sense if you think about it, because this is exactly the same. What left shift 5 does is multiply by 32. Sorry, that should be count. So basically this first bit multiplies count by 33. This bit does it times 32, and then we add it once more, and then we add a letter. And the reason why it does a shift is that it is a much faster operation. for the CPU. Although I'm pretty sure that some clever compilers now will calculate that for you automatically. And different languages have a slightly different variant here, and it depends a little bit about a specific use case which hash function might work slightly better. But at least PHP implements internally this hash function. Just making sure that iClave is correct. And now if you run this, you should get them again in a different order, which is indeed what happened here, because of course our way of hashing has changed. Now it'd be great at some point to actually compare all these hashes and see what is the best way of doing it for a specific use case, like finding all the words in the English language. But that is something that we leave for maybe a future episode. I've come to the end of this video. The hour is full. Are there any questions that you'd like me to answer before I say goodbye for the day? All right. No questions then. I would say thank you very much, and I'll be back next week.